Okay, today's guest is Dr. Eric Cramer. He is visiting us from Melbourne, Florida. He received his Bachelor's of Science in Physics and Applied Mathematics from CUNY, Queens College, and his Master's in Space Sciences from Florida Institute of Technology, and his PhD in Physics also from Florida Institute of Technology. And his PhD was on electron avalanches inside the high field regions of thunderclouds. He is now working as an engineer in industry, and he was also a postdoc research fellow. He was an NSF recipient, and he did his postdoc at University of Alabama in Huntsville, and he worked with NASA there. He was also a postdoc research scientist at FIT, and he will be talking today on the physics of lightning over land and the ocean.
Thank you. So thank you, Sam, and thank you for the department and the School of Atmospheric Science and Marine Science for inviting me to give this talk today. I'll start off by saying that I'm not an atmospheric physicist. My background is really in particle physics and modeling high energy physics, but along the way, because of the field that we're in with lightning research, I picked up some atmospheric chemistry and atmospheric dynamic skills, and obviously worked with a lot of close meteorologists from Florida Tech, from University of Alabama, engineers. It's a very big, large collaboration for this field. And so by the time I'm done with this talk, I hope to give you a flavor of not just what we see in terms of lightning, but what we don't see in terms of lightning, how the radiation and all these different high energy events that happen with lightning. So I'll give you kind of a flavor of the overall effort in the field. So I just want to give some acknowledgments to I have some highlighted names here. Dr. Rasul from Florida Tech was one of my PhD advisors. Joseph Dwyer, who's my main PhD advisor, moved to the University of New Hampshire. And my postdoc advisor, Michael Briggs, who's associated with NASA Marshall Space Flight Center in Huntsville. And I want to give acknowledgments to the entire University of Florida team, which I'll be talking about the experimental effort that we did for studying lightning on the ground. So here's just an outline of the talk. I'm just going to give an introduction to lightning and what exactly is high energy atmospheric physics, and some aspects of what I've done in my PhD with the ground observations, and my main project, which was really just looking at theoretical models of X-ray and propagation inside thunderstorms. And I'll talk about some of my postdoc work, which was looking at terrestrial gamma-ray flashes and some satellite data observations of these bright flashes of gamma rays emanating into space. And I'll briefly touch on, since I know this is an atmospheric science department, two topics, TGFs on land and water, and also how TGFs are associated with tropical systems. So kind of a little bit of an interest to you guys, I hope, at least as we go through this. And I'll just give a summary. So why do we care about lightning in the first place? Well, lightning, as you know, living in Florida, is one of the most destructive forces on Earth. It produces a lot of damage in the U.S. Every year, about 4 to 5 billion in losses in damages. And every year, lightning kills about 100 people in the U.S. alone, and that's more than hurricanes and tornadoes. So if you were looking at this picture in real life, you really should be more scared of the lightning flash than the tornado. And of course, I'm preaching to a bunch of atmospheric physicists who are studying tornadoes and hurricanes. But also lightning goes along in the same kind of destructive phenomenon. So just a little bit of background, how lightning 101. So there's a lot of different theories of electrification of thunderstorms, but what's well agreed on is that you have warm air that rises into a cloud, producing ice particles. Those ice particles collide with hail particles or grapple inside the thunderstorm that are moving down in the cloud, and then they collide and you get separation of charge. And inside of a thunderstorm, there are typically 3 different regions of charges: a lower positive, a middle negative, and an upper positive region. And there are different types of lightning discharges. What we're all familiar with was cloud to ground, which is the lightning that will get you on the ground. But there's also, within a cloud, you get intense lightning flashes between the upper positive and the middle negative region. And cloud to cloud lightning can happen, and also cloud to air. And one of the most dangerous lightning bolts is called bolt from the blue. So that's where you'll go outside like today, a blue sky, and all of a sudden you get hit. And so what happened? The storm was miles away, but you had enough of the formation of the cloud in the upper part of the atmosphere that the positive charge was able to escape and into virgin air and hit you miles away. So lightning can travel up to 20 to 50 miles from its base. And so typically what we see on the ground is negative cloud to ground lightning, which means that you're depositing negative charge to the ground. Positive cloud to ground is significantly rare. Negative cloud to ground is about 95% of all lightning strikes. So for the typical current amplitude of a negative lightning strike is about 30 kiloamps of electricity and of current. And for a positive lightning strike, it's about 300 kiloamps. So extremely more current inside of a positive strike, because you have to go through more air to get to the ground, and you have a larger potential difference to do that. So positive lightning is interesting in itself because, again, it relates to, and I'll talk about a little bit about the high energy phenomenon, but to get really positive lightning onto the ground, if you have enough wind shear in the top of the cloud and top of the anvil to kind of unscreen the positive charge from the ground, that's when you really get a positive flash. So that's just the structure of a thunderstorm. And this is an image taken from NASA's LIS sensor, showing basically the average lightning flash rate per year. So you can kind of see per kilometer squared per year. So really in the tropics where you have mostly abundance of thunderstorms, Africa, which is a really hot spot for lightning flashes. So we use optical sensors like this to kind of give us an idea of how intense and where lightning is occurring on Earth. Also from lightning, so I'll talk a little bit about VLS signals. So this is a snapshot. Let's see if I can play here. Not really well frame rate here, but it's known that lightning emits radio waves in the very low frequency range of about 3 to 30 kilohertz. And so these radio signals from lightning are termed spherics. And a group at the University of Washington in Seattle had deployed a network of these lightning sensors around the world. And so what's just called the Worldwide Lightning Location Network. And they're shown here in red circles. So here are some of the locations on Earth, and all the blue here are the radio signals that are being detected from those receivers. So we can get a lot of information from the radio waves that are generated by lightning. And again, that'll be useful later on when I talk about the radiation effects. And here's just an example of what one of these radio signals looks like. So there's these pink lines here. Each one of these pink lines is a spheric, or a single radio burst detected from lightning in this frequency band. So just a sample. You can go on the Woolen website and actually download some of the lightning data that's available there. Another sensor that was deployed recently is the Geostationary Lightning Mapper, or GLM. And it's basically the first lightning mapper in geostationary orbit. So it can kind of look at the evolution of a storm as it's strengthening or weakening. So here on the right here is an image from Tropical Storm Alberto on May 27th to 28th, 2018. So you can kind of see as the storm kind of develops, you get really intense lightning flash rates on the outer rain bands here as it's strengthening, and as it weakens, the lightning rate falls out. But so basically collects information such as frequency, location, and extent of the lightning discharges to identify intensifying thunderstorms. So really useful information in terms of like optical signals and where lightning is occurring on the globe. So that's a little bit about the signals we detect from lightning, the optical energy that we detect from lightning. But what you would not intuitively know about lightning is that there are many other high energy, what we call high energy phenomena that are associated with lightning. So lightning is occurring down here in the troposphere, but actually in the stratosphere we have a lot going on in response to the lightning flash. And what I'll talk about today is just one piece of the high energy puzzle, and that's these high energy electrons and gamma rays that emanate into space. So these are called TGFs. There's other events called sprites, and these are just cold plasma that are in response to the lightning discharge. They were first discovered from the space shuttle when astronauts went up there.
What is cold plasma?
Well, it does so. While lightning has a really hot channel, the sprites don't have that. They have a cold So if you would look at it, it would be
Is it electrons or is it other particles?
electrons and ions, yeah.
Okay.
And they can reach up to the ionosphere. And then we have also these other events called halos and elves. So if you ever look in a clear night, you can actually see these from the lightning strike. You kind of see these glows on the top. And we have a camera set up on the Florida Tech roof, and we've captured tons of these events. But there's a lot of research in these areas, and I'm not really an expert on those types of high energy phenomenon. But I'm going to talk today about the electron beams and gamma rays that are being detected. So just the flavor of what this field really is in terms of just not just atmospheric lightning, but also high energy particle physics. So a negative cloud to ground lightning strike happens when you have, so again, like I talked about, you have the positive and negative layer, a negative, middle negative, lower positive. So when the lightning, negative cloud to ground brings negative charge down to the ground. So you get these, as the channel propagates towards Earth, you get these you get these streamers, basically, these branches that carry negative charge. And so in response, when the potential is really high, you get basically an upward positive streamer from like a tall building or from a structure that meets the negative downward strike, and then you get an attachment, what's called an attachment, when the negative leader meets the upward positive leader. And this is called the negative step leader, by the way, and that'll be important in a minute. So then in this stage, basically you have an attachment, and then you have a return stroke. You have charge that's being deposited back up to the cloud to neutralize all the negative charge that's being brought down to Earth. And then you have a moment where you have a channel that reminates, but you have what's called a continuing current. So you have continuous current that moves, and then you have another sequence where negative charge comes down, and that's called the negative dart leader. And then another return stroke. And this can go on for 2 or 3 cycles within one flash. And the time scale here is on the order of tens of microseconds in terms of how this process occur. So you need really fast equipment if you want to capture this.
So Eric, is my next lightning question.
Sure.
One thing I always wondered with these kinds of discussions is, so when you say the upward positive leader, what does that really mean physically? Because I mean, it's only electrons that are flying around, right? So what's actually coming up?
So you have so you basically have, so at the tip here, you have a really high concentration of electric field. Okay. So you're breaking down the air. So you have kind of these ions that are propagating back up and meeting the electrons.
I mean, it is positively charged particles?
Positive charged particles. Mm-hmm. So the problem with lightning in general is that, this is all fine, but you never know when and where lightning is going to strike, right? So if you want to study it in a repeatable scientific manner, you need a way to harness it. So part of my effort as a PhD student was to help out at the International Center for Lightning Research and Testing, which is a facility that's owned by University of Florida. And what we did was we gave it a place to strike. We did rocket-triggered lightning. So the only difference between this picture and the picture that I showed previously is that the initial stage, we don't have that negative step leader that's coming down from the cloud. We're basically giving it a point where the positive, we're giving a positive stream, positive charge leader, upward positive leader, and then eventually we get an attachment. But there's no initial movement of negative charge that's coming down from the cloud naturally. So that's the difference between natural lightning and rocket-triggered lightning. And so we would fire this rocket. They go about 300 meters or so into the air, and you get an attachment. And so you would get a lightning strike that was harnessed in a location where you can study it. And here's an example of one of the model rockets that we used. We had a copper spool on the bottom of the rocket, which would act as the conductor. So as the rocket is launched up, you'd have a very high, then the positive streamers will be on the tip of the rocket cone. That's where you'd have the upward positive leader emanating from. So basically gave it a place to strike. So here's an example video of a rocket-triggered event. And then I'll play it again in slow motion. And we're using high-speed cameras here up to about 500 frames per second to capture the optical energy in the lightning flash. And so what you're seeing there is basically, here's the picture on the left. So each one of these branches here is an individual return stroke. So that's the sequence where we're depositing energy back and forth from the cloud to the ground. And the green here is the actual copper burning of the copper wire of the rocket burning, the exploding triggering wire. And so this was a repeatable experiment that we did, and for optical images and as well as electric field measurements and current measurements from lightning, try to measure peak currents. And here's on the right is another example of a little further away shot where we see the green exploding wire and then the upper channel of the upper sequence of the return strokes. And so what this actually looks like if you measure the current, this is the waveform that you would get. There's some features where you see these very high current pulses from the upward positive leader. And these were important for University of Florida to try to understand peak currents, electric field measurements inside thunderstorms. And then we use these to guide us for the X-ray measurements, which I'll show here in a moment. So here's some of the instrumentation we had on the field. So we had like 24 of these stations, and one station would encompass an electric field sensor, some of these electric field mills that we pointed out before, the electric field flat plate antennas. We also had muon detectors to detect cosmic radiation coming from thunderstorms, and we had X-ray detectors. And I'm going to talk mostly about the X-ray detectors here. But again, we had very high-speed cameras. One of the cameras went up to 1 million frames per second. It's extremely beautiful photography that was accomplished there by the grad students at UF. So, but our main focus University of Florida was doing the measurements of electric field and peak current and maintaining the field. We, as Florida Tech, came in and built these radiation detectors. So what they are, it's called a thunderstorm energetic radiation array, or TERR. And there were 24 of these boxes over this site, and they contain 2 photomultiplier tubes in each box. A photomultiplier tube basically it housed a sodium iodide crystal. So when a photon would hit the crystal, it would convert that energy to an electrical signal, which we can then measure on an oscilloscope and get the waveform of these X-rays being emitted from lightning. And so one of them you can see is unshielded, and one of them is shielded with lead. The lead is a really great absorber for X-rays, so we're able to get some energy spectral comparison between soft X-rays and harder X-rays to gamma rays by using just shielding of lead. And these detectors were good up to about 1 MeV or so. The lanthanum bromide detector on the right here was a much more sensitive detector. I believe this went up to 10 or 20 MeV. So each one of these boxes then had 2 of these tubes, had the electronic controllers where we converted the electrical signal into fiber optics, outputted that into a receiver, into a trailer that was a central trailer that housed all the scopes for every single one of these boxes across the field. So these were our X-ray instruments, and this is the field that I'm talking about. So it was a 1 kilometer squared field. I don't know if anybody knows where Camp Landing is. It's a National Reserve, National Guard reserve, right in the middle of the state. It's between St. Augustine and Gainesville. Really nothing much around but a state prison. So the National Guard gave us this land basically to run these experiments. So every time we would fire one of these rockets, we'd have to call in advance and let them know that this is looks like a good day for thunderstorms. We might be firing 5 to 10 rockets. So again, these show some of the stations. The tower launcher was located here. This is kind of an older Google image. I didn't have time to put a new one in, but this was again a collaboration between Florida Tech and University of Florida. So okay, so we have these boxes, right? So we throw these boxes there, and it was before we did this experiment. It was theorized that sure, lightning is encompassed with high electric fields. You can get X-rays and gamma rays from electrons that are free that can emanate those gamma rays. So what did we see? We saw basically very distinct X-ray signals from a lightning flash. So on the top here, top left, is a cesium-137 gamma ray source. So this is our calibration. So we had like these little microcurie sources that we would put on the detectors, and they have cesium has a very distinct line at 662 keV. So we knew for that photomultiplier tube that 662 keV corresponded to a specific voltage. So then that was our calibration. So when we put this out in the field, we saw X-rays at very distinct energy levels, all the way up to 500 keV, up to almost 1 MeV in energy. The problem with detecting photons with these scintillators is that if you get a really large flux of gamma rays hitting the detector at once, you kind of blind the detector. It's called a pulse pileup in dead time. So you get a bunch of photons that are that are hitting the detector faster than its response rate. So you can kind of get a period where you don't see anything and kind of blinds the detector. So filtering, and part of the data analysis and modeling, we had to take that into account when we try to do a one-on-one comparison. On the right here is the is X-rays from the step leader, kind of similar to here, and also in the same time we had an electric field sensor. So we kind of saw that as the electric field changed, so as the lightning leader approached the ground in steps, we would get a burst of X-rays with each one of those steps. So we were able to coordinate between the lightning discharge and the X-rays. And yes, the actual lightning discharge itself is producing these X-rays. So so when I came in and started as a grad student, my advisor had the idea of, okay, so we have these X-ray signals, but what would an actual, we saw the X-rays being emanated from the lightning, but we wanted like optical proof that we had X-rays with the lightning leader as it was approaching the ground. So what we did was built a X-ray camera, and so this is like an artistic image here, the X-ray camera being pointed towards the tower. And what this really encompassed was 30 of those photomultiplier tubes and a hexagonal structure. So basically, it was an X-ray camera that had 30 pixels. So you think about your smartphone of gigapixels. It was very low resolution, but this took 1 million frames per second in timing, which is what we need to capture the X-rays from the lightning bolt. So we housed this into a aluminum structure and then encased it in steel. But the problem with X-rays again is that, or these detectors, X-rays don't care about angle of incidence. They'll, you put this detector on the field, you get X-rays from all different directions. But what we really wanted was, we were pointing this to the tower, we wanted to see the X-rays directly from the lightning strike itself. So in order to accomplish that, we had to house the entire instrument in lead, over a centimeter thick in lead. So we had to go and bolt this to the structure. And basically what we really wanted to understand was, what would Superman see if he was looking at a lightning strike? That's kind of what the idea was of this whole experiment. And we spent the entire summer in the machine shop, spent the entire time in the machine shop welding this box together, putting the lead on. The problem with lead is it's very soft and Florida is very hot. So we would leave this outside, we'd come back the next day and we'd have to one bolt would be kind of warped, we'd have to warp it back into place. So lead is extremely hard to work with. I would not recommend it. We built the electronics for all the photomultiplier tubes for the X-ray camera, as well as the initial, this was the second version of the X-ray camera, but we housed all of the oscilloscopes inside these truck trailers. So we had, I think, 3 or 4 LaCroix wave oscilloscopes to detect the X-ray signals, and it was cooled by an air conditioning vent here. So it's kind of, this is the fun, this is the stuff that we made for grad school, PVC truck boxes, and kind of bolted it all together. So in the end, what did we see? So this is showing the computer, the data analysis. Once we got an event on the ground, we were aiming at the tower again, and we can see that the higher energy X-rays are moving with the white hexagon structure here. The black is where it had no signal, and light green, the darker green, is higher energy X-rays. So you can kind of see as the lightning is approaching the ground, we get the highest amount of energetic radiation being emitted with the lightning here. So that was a little bit about the experimentation. So I want to talk about the theory. So how do we even get X-rays in the first place from lightning? Just to remind you guys of the electromagnetic spectrum. The electromagnetic spectrum goes from radio all the way to gamma ray. So for radio, we have very long wavelengths, meaning the distance between the repeating cycles. And for gamma rays, where we're interested in looking at X-rays from lightning, we're in the very high frequency range, so very short wavelength. And so electromagnetic radiation can be viewed as a wave, and it can be also viewed as a particle. So the particle equation is E equals h nu, which is just the energy of that individual photon, how that's related to the frequency, or inversely to the wavelength. So when I talk later on in terms of energy, basically radio waves are down here at the nano electron volts, and gamma rays are mega electron volts. So that electron volt is how much work's required to move an electron over 1 volt. That's what an EV is. So when you different groups of people talk about electromagnetic energy differently, either wavelength, frequency. If you're an engineer, you talk about frequency. If you're a physicist, you talk about wavelength. But for the purposes of this talk, I'm going to talk everything in terms of energy, E. So again, frequency nu here, relating to lambda, speed of light, and then we have Planck's constant that relates the classical interpretation of how to view light to the quantum mechanical version of the wave-particle duality of how to view light as a particle. So some of the basic interactions that electrons and photons interact with air from left to right here. So I'll go over electrons first. These two are for electrons. So what's called molar scattering. So if you have a very fast or a free electron that's accelerating, it can knock off another electron on an orbiting molecule or atom. And so that collision process is called molar scattering. So you get more of these energetic electrons being knocked off from an atom. How you get a photon from an electron? So as an electron approaches an air molecule, it can slow down, and that braking force it transforms the energy of that braking force into a photon. So you get an emission of an X-ray, which is called Bremsstrahlung, which is German for braking radiation. So the electron slows around the air atom, and then you get an X-ray. And so for photons, what's important is Compton scattering. So you can have a incident photon that hits an electron, which will change its wavelength or its energy. So you'll get scattering of the photons as well. So that'll be important later on when we look at the how much energy we're getting from the satellite measurements is mainly dominated by Compton scattering. And then pair production. So an interesting fact too. So if you have X-rays, you have high energy electrons. You also can get antimatter. So it turns out that thunderstorms are a prolific producer of antimatter. So as a photon approaches the nucleus of an atom, it can split into a positron-electron pair. And again, that'll be important for the theoretical models. So as a PhD student in here, and this image cut off, so apologize for that. But as a PhD student in here, there's probably one aha moment in your career that you'll go through that you're struggling on a problem, you're looking at something for days or nights on end, and you're like, well, why didn't this click? And so it's cut off here, but what this is trying to show is the solid blue curve. So the y-axis is the force on the electron, and this is the energy of the electron on the x-axis. So force versus energy. And so the solid blue curve here is the force that's experienced on an electron as it goes through air, the frictional forces, all the drag and frictional forces as it's trying to go from point A to point B in air. The red solid line here is a uniform constant electric field, so it's the electric force. The dashed line here is shown is the effects of Bremsstrahlung. So if you have a free electron that's inside of an electric field, say of 10 keV per centimeter, it'll experience the frictional force, but at some point at epsilon th, it'll gain energy from the electric field. So the energy that it gains from the electric field, it will overcome the frictional forces that's experienced in air, and then it can accelerate into relativistic speeds. So you have from the electric field. But at some point at epsilon max, the energy is so high that it loses all of that energy if it undergoes a Bremsstrahlung collision, it'll deposit all that energy into a photon and kind of just disappear, go away. So this process is called relativistic runaway electron. So a relativistic runaway electron is dependent on the electric field that's being applied to that electron. So as the electric field increases, more of the low energy population of electrons can run away because the field is strong enough. So you get kind of thermal low energy electrons that can run away as well. So it's a complicated plot, but my aha moment was here, basically defining this epsilon max, because this wasn't defined previously. And when I was trying to solve my equations, I was like, why isn't this working out? There has to be an upper bound to where the most an electron can accumulate energy from the electric field. So this solid blue curve could be shown here. It's a very complex equation relating to the density of air, the atomic number, the atomic radius, the electron radius, and the rest mass of the electron. So just to keep in mind, we go through.
At epsilon max is the mass of an electron?
No, so
c squared.
Yeah, yes, approximately yes. Mm-hmm. Correcting for relativistic speeds, though, you have to correct for the gamma factor for relativistic motion. So we have these electrons that are running away now in an electric field. So we can define a mean free path. That is to say that at some distance, depending on the electric field, if you have one runaway electron, it can Molar scatter, like we talked about with scattering off of an air atom and producing another electron. It does that in an exponential manner. So if you start with one electron, if you go over a distance of say 20 meters for say a 500 kV per meter field, it'll produce E more electrons at that distance. So it's kind of a mean free path of how you get the mean free path of a runaway electron. And so this falls off as the electric fields increase, like I talked about. So the higher the electric field, the more that low energy population of electrons can run away. So the more electrons you have for higher electric fields, so the shorter the mean free path becomes, where you get more of these runaway electrons. So that's kind of the exponential process of getting these electrons. And so this is a model, this is a simulation model showing how to produce one of these relativistic electrons. So you start with one electron that, say, gets knocked off by a cosmic ray. So you have like solar particles or hitting the atmosphere, producing cosmic rays. Those cosmic rays can knock off that initial electron inside of a thunderstorm. That electron then runs away in that electric field, which is pointed upward here, in the opposite way of the electric field. And as it travels along in Z, it'll produce more of those runaway electrons. So you get an avalanche effect. So now you have a whole population of electrons that are moving at relativistic speed and have very high energies. And we call this a runaway electron avalanche. And so here is an actual just run of the simulation. So we start with one seed electron here. In this case, the electric field is pointed downward, so the electrons move up. And you see this plume of electrons that get produced by just one runaway electron. And again, we're assuming here a constant electric field that's pointed downward. In reality, inside of a thunderstorm, electric fields are very complex. They can be diverging. They can be doing all different sorts of things. So the actual beam of electrons doesn't have to particularly be vertical. It could be tilted one way. It could be horizontal. The fact of that is we just don't know for the observations. But the physics here is that you get this population of electrons on the left here, and on the right is kind of showing like energy space. So how the electrons are losing and gaining energies as they move through the electric field. So those are electrons. So as those electrons move again in the avalanche, then they'll produce those X-rays. There's two different competing theories in the field of how to get those electron avalanches. What I just showed you in the models that I've been using, we assume that the avalanche is produced in the charge layers of the thunderstorm. So if you have a negative and positive charge region, like I talked about earlier, you have that electron acceleration happening in that region, kind of like more of a global scale inside the thunderstorm. There's also a theory that, and like we showed that X-rays are being emitted from the lightning leader tip too. So there's also a theory that you get the avalanches from the very high electric fields of that lightning leader as it propagates to the ground. They're both related, kind of looking at different processes, but in my opinion, both are involved in terms of the generation of X-rays and gamma rays. And this model on the left, what it leads to is a feedback effect, and I'll describe that here in a moment. So here's our avalanches, right? So initially, it was thought we have a runaway electron. We have one runaway electron. You get electric field. You have the electric field. The electron runs away, and you get one runaway electrons. Then we talked about the avalanche, right? So we get molar scattering, and the flux now of runaway electrons increase substantially. Now with the large scale model, you get what's called feedback. So the electrons then can produce positrons, like I had mentioned. Those positrons now travel back to the original point because they have opposite charge, back to the initial point of where the electron avalanche was created, and creates more electron avalanches. So you get this feedback effect where you're getting now many avalanches of runaway electrons. And also, by the way, positrons as well as X-rays can then also produce another electron, which can then add to this effect. So you get basically this multiplication factor of runaway electrons, and the flux of the number of runaway electrons in this whole process can reach up to like 10 to the 18. So very fast process and a very high abundance of energetic particles. So my advisor came to me and he said, okay, so we have this Monte Carlo model, it's great, but it's a black box, right? You have some input, like the electric field strength, you give it the number of electrons, and it's Monte Carlo based. So if you give it 1 or 100 electrons, as long as you run the simulation over a certain number of steps, number of times, you get a statistical significant number of particles, then that's the point of the Monte Carlo, because you can't simulate every single interaction that every electron goes through. So it's easier just for like 100 electrons at once, simulate one at a time, then stitch all those runs together and have a statistical population. So he came to me and said, okay, it's great. This is a great tool. We were matching with the observations, but can we describe the output of the Monte Carlo in some kind of simplistic way in terms of some kinematic formulas? So we went back to basics and we looked at a transport equation. People in here probably are familiar with any transport equation that you can think of. But so what we wanted to look at was the electron energy distribution. So after this electron avalanche plumes, it reaches a steady state. And at that steady state, it has some electron energy distribution, some spectrum. And so we can output that from Monte Carlo. But again, that doesn't give us really much information. We wanted to know what's the actual physics. So this is the equation that my advisor and I came up with. We have the number of electrons per unit energy per unit time on the left. This term rate, it basically describes all the energy losses that electron experiences as it travels in the electric field. And on the right is the source of new runaway electrons, those backward propagating positrons and gamma rays that I talked about, where you get a recharge of those runaway electrons. So this is simulation results here for a 400 kilovolts per meter electric field. So when I quote these numbers, these are sea level equivalent electric fields. Everything scales with the density inside of a thunderstorm. So we modeled everything at sea level and then kind of adjusted from there. The runaway electron avalanche model, so the little dots here are the result of the Monte Carlo simulation, and the blue, red, and purple dashes are solutions, analytical solutions to this equation, assuming certain things for the rate of loss of energy per unit time, or the total force. So we can approximate those equations that I showed you before, are very long, complex, kind of hard to solve analytically. So we can make some approximations in those equations to come up with something that we can look at analytically. And on the right here is the scattering angle. So at the end of this electron avalanche, how much are the electrons scattered from the vertical line? So as the electric field strength is increased, the electrons become more forward beam. They don't scatter as much because they have more energy, and so they continue to go in a straight line. So just some properties of the simulation that we wanted to analytically characterize. But if you look at this plot here, when we added the effects of the Bremsstrahlung, so the X-ray generation from the electrons, you notice that the analytical formula did not coordinate at all with the Monte Carlo simulation. So again, the Monte Carlo simulation for this study is like our data. We're trying to replicate what the Monte Carlo is producing. So we added more physics, and we're scratching our head is, well, why isn't it matching the simulation as we added more physics? And the solution was that we forgot a diffusion term. So as the electrons propagate, they also diffuse in energy space. So they're accelerating and decelerating and colliding with other air atoms. There's a diffusion in energy space that needs to be taken into account. So when we did that, the effect was we can look at that diffusion as a probabilistic as like a Gaussian process. And so what we did here on the left here is this is for a certain energy of an electron. It has some probability of losing all of its energy or gaining double its energy. And so you can put this into you can model this and then calculate what the width of these distributions should be. And what's really nice is that the width of the probability of distribution can be related to all the processes that we talked about. The molar scattering component, which goes like the energy of the electron squared, the Bremsstrahlung factor, which goes to like energy cubed, and this is an empirical fit because Coulomb scattering, which is how the electrons are deflected in those angles that I showed, it's a function of both the angle and the energy. So it's kind of a complex function. So basically we can write on paper what the width of the distribution is and calculate the diffusion coefficient analytically. And when we did that, we matched with this Gaussian convolution. We matched exactly what the Monte Carlo was giving us. So the whole key was really this diffusion in energy space. So
what's on the y-axis of that chart?
Yeah, so this is the number DNDE, the number of electrons per unit energy. So it's like an electron energy spectrum here versus energy. Okay, so then so we have these electrons. We looked at the energy spectrum, and this is showing what happens after you take those electrons, and then those electrons inside the thunderstorm will produce photons. You take those photons and you propagate them through the atmosphere to see what would actually reach space. And so what you're shown here is the pink are the gamma rays emanating from the atmosphere, and the orange and green dots here are electrons and positrons that are following the magnetic field line. Of course, photons don't care about magnetic fields, but electrons and positrons will escape the atmosphere and ride along those magnetic field lines. So what these are termed are terrestrial gamma-ray flashes, and they've been observed by satellites, NASA satellites. So here on the right is a snapshot of what a TGF looks like. These are the number of counts in hundreds of microseconds versus time, and so you see a very short burst of signal here of gamma rays, and this was detected by the BATSI, which is the Burst and Transient Source Experiment. So basically those scintillators that I showed that we use on the ground, this instrument used those in space to try to detect gamma radiation coming from distant galaxies. They turned on their detectors and they found this flux of gamma rays hitting them from the Earth, and within the second week of turning on the instrument. So they were scratching their heads and said, well, there must be something wrong with the instrumentation, or the geolocation must be off. But no, they saw these events happen, and it was then understood that, okay, we're getting these gamma rays from thunderstorms. So original gamma ray astronomy mission turned into a terrestrial astronomy mission, basically. So and TGFs, and there's a bunch of papers on the research, so I don't have time to go through all of it now, but basically those plus IC lightning, those inner cloud lightning discharges that I mentioned earlier in the talk, where you have the positive lightning in the cloud, those are the prolific generators of TGFs. And so there's a ton of papers on that. If you're interested, you can come ask me for some of those references. So that was the burst and transient source experiment. So during my postdoc at University of Huntsville in Alabama, they were the mission operation team for Fermi GBM, which is the gamma ray burst monitor. And so what this is a detector that's in space now. It was launched in 2008, and it contains 12 of those sodium iodide detectors that we used on the ground, 6 on each side of the spacecraft, looking at different orientations of the sky, and 2 bismuth germanate detectors. So just like the lithium bromide detector, this detector is really sensitive and go up to 40 MeV in energy. So we have 2 of those on board, 1 on each side, and 12 of the sodium iodide detectors. So my mission basically in Huntsville was to look at the data that we got from the TGF data that we got from the satellite. On the left here is from our Fermi GBM Catalog, and these are all the TGFs that were detected in the South American region here, and you can see all those pink spots are the actual locations of the TGF that detected by GBM, and on the right is shown as the green squares, the green stripes there, are radio locations from Woolen. So like what I talked about before with the radio. So we were able to look at the footprint of Fermi, which is the red circle there, for a single event, and see where lightning was occurring underneath the spacecraft footprint, and determine which of the storms within 10 milliseconds time delay, which one of those storm clouds produced the TGFs. So we now have radio locations of the storm that produced the TGF, and we have the satellite gamma ray observations. From that, and here's another example too from another detection network I just wanted to point out, because at Florida Tech we have one of these receivers on the roof of our building. So what you're shown here is the red circles are GBM TGF locations, and blue pluses are the NLDN locations. So we know how far the satellite is from the source of the TGF, which kind of constrains the model when we try to model these things. So here's a snapshot of the what the actual satellite sees. So the problem with the satellite again is it's blinded by this. It also has the problem of dead time and pulse pileup. So you got a flux of these gamma rays hitting the detector at once. It blinds the detectors. And in an average event, we might only see 12 photon counts. So So it's not a very, it hurts the modeling efforts because it doesn't give us really statistical significance in trying to adjust the parameters of the model. And the bottom is the counts per keV per microsecond versus energy. So it's sort of like the photon energy spectrum. Red here is a model that we used, a photon propagation model, and black are the data results. So trying to model a TGF from an observation of Fermi GBM, like I said, the problem is pulse pileup, dead time from the instrumentation, and also some of the free parameters. So the main goal of modeling is we want to understand the physics of the thundercloud, what's happening, how the electrons being generated. But in order to do that, we have to backtrace from the photon observations we're getting from the satellite. And like I mentioned before, those photons could be emitted at any arbitrary angle, depending on the structure of the electric field inside the thunderstorm. We do know the location of the spacecraft relative to the photon beam because of the radio signals that we get. But some of the other free parameters are the electric field strength and the beaming geometry of how these photons are beamed onto Fermi. So it's a very complex problem in trying to individually matching energy spectra from one single event to the models to try to understand the electron acceleration. So we attempted to do that though. So we have basically what my task as a postdoc was to, from all the models I used in my grad school research, from all those electron models, take those and propagate them through the atmosphere. Two-step process. Generate the photons in the thundercloud, then propagate it through the atmosphere, where Compton scattering takes a large role. So as the photons emanate through the atmosphere, they're going to scatter in the atmosphere, and then the lower energy photons will arrive later to the spacecraft. You can actually see that in the time profile. But here is a simulated energy spectra showing that. So basically you get this bump here at the very low energy. This is a number of photons per unit energy versus the photon energy. And you get an abundance of these Compton scattered, very low energy photons reaching the spacecraft. So this is assuming that you're at satellite altitude at like 500 kilometers, which is where where Fermi sits. So basically, and then you also see the 511 keV line. This is the positron annihilation line. So as I mentioned, that we have positrons, electrons, and photons being propagated all at once. So in the model, this is kind of a sanity check. Do we get an annihilation line? And we do at 511 keV. And again, this is shown for different electric fields, source electric fields inside the thunderstorm. So it becomes a very complex problem because you can start with a relatively low electric field at 300 kilovolts per meter, and start with a deep source. So let me go back to one more slide here. The other factor I forgot to mention is how deep is the photon beam in the atmosphere. The deeper the photon beam is in the atmosphere, the more absorption you get, and the higher energy photons you get at spacecraft altitude, because those are the only ones that can really escape the attenuation of the atmosphere. So I put together this propagation, these models, and again, for low electric field and a relatively deep source, you can kind of see only really high energy particles hit the spacecraft at once, and so you can kind of tune the parameters of the model and then compare it with the actual GBM data. So this is a summary plot of the number of electrons versus the offset of the TGF with respect to the spacecraft. So each one of these dots represents a single Fermi TGF event that we detected, and for different source altitude models, ranging from 11 to 20 kilometers. So, and the red here is what we call a narrow beam, meaning that the physical angular distribution that I showed in that plot, that would be the angular distribution that those photons are emitted at. But again, if the electric field isn't constant, if it diverges, those angles will then be dispersed in a wider cone. So the red is basically assuming that you have a wide beam of photons, while black is narrow beam of photons. So and you can kind of see that the number using the Fermi data, using the models, we can backtrace to what are the actual number of electrons in the thunderstorm had to be in order to produce the observation. And you can kind of see they all kind of align around 10 to the 18th, which is what I mentioned before, which was the flux you get from the relativistic feedback effect of the large scale positive and negative charge layered model. So again, it's a complex problem because you have different you have different parameters that you can tune in the models to try to match the observations. So, and just really quickly, a couple more slides. I just wanted to go over some studies that have been done recently on characterizing lightning over land and water. So this was a study done by Professor Nag, who's he's like the main lightning professor at Florida Tech right now. And he took 50-kilometer circles off of what he called ocean and deep ocean, and two 50-kilometer radii off the east and west coast of Florida. And he tried to compare the duration of the leader strokes and also the peak current of the lightning stroke. So basically, I'm not going to go through all the details of his analysis, but what he concluded was that shorter duration over ocean supports higher return stroke peak current. So you have higher peak current or more intense lightning over ocean than you do in land. And that's at least what his study produced. So coastline distribution of TGFs. So here's Fermi. These are all the Fermi TGFs in a 3-year period over December, January, and February, and over January, June, and August from 2013 and 2014. Blue dots here are TGFs that don't have a radio location, and the yellow dots are TGFs that have radio locations to them. So you can see that a lot of TGFs occur over the coast, over land, a ton over water. But the if you do a statistical distribution of if you look at all the TGFs that are greater than 100 kilometers from the coastline over water and greater than 100 kilometers over land, you see that the number of TGFs we get over ocean is much larger than the TGFs that are produced over land. So that's basically the summary of this plot. We also noticed TGFs are hurricanes are prolific producers of TGFs. We've seen TGF production in this is Hurricane Paula, I believe, or Tropical Storm Paula, and you can see here on the left this is a radar image or an optical image, and you see the plus sign here. This is the location of the TGF. Yellow are lightning strikes within the storm. So hurricanes have prolific lightning on the outer rain bands of the storm. So we were able to detect from Fermi, we were able to detect 2 events here of TGFs. And so what this plot's showing here is this is the time of the TGF that occurred, and the time of the TGF seen by Fermi, and the blue to green to red dots show the strengthening of that tropical storm. So it seems that TGFs are associated with the strengthening phase of a hurricane. So as the hurricane is strengthening, we get these gamma ray bursts that are observed on Earth, observed by satellites. And so you guys should be familiar. So my joke is you guys are also prolific producers of TGFs if they're emitted from hurricanes, since University of Miami hurricanes. So, and then one last observation that we made on. So this was the eye wall of Hurricane Patricia. So this isn't a satellite observation, but this is an actual aircraft measurement. So we took some of these gamma ray detectors, put them inside an aircraft, flew them through the storm. And so what you're seeing here is a radar image of the storm itself. The blue, the dotted circle here is the path of the aircraft. These black stars are lightning detection radio signals from not Woolen, but the Earth Network Lightning Detection System. And the red circle here is detection of lightning from Woolen. And the main point of this study was we were trying to understand what caused the TGF, since we had an in situ measurement. There's a first observation inside of a hurricane eye wall. So the on the right here shows attempts of modeling the data, and what we found was that the aircraft was lit up with positrons. So as the aircraft was going through, we had a TGF that was detected, and the TGF then produced a beam of positrons that emitted backwards towards the plane. So you had basically the plane was radiated with positrons. So just some interesting little tidbits on how we're relating the high energy phenomenon with the meteorological characteristics of hurricanes. And one last study that I did, it's natural you have all this radiation in the atmosphere. Is it harmful to the atmosphere? Is it harmful to humans? I didn't show in this presentation, but we showed that it's very rare to be in one of these beams if you're inside an aircraft. And I showed kind of we intentionally flew into one of these things, but in a normal aircraft, pilots stay about 20 miles away from thunderstorms. And so to be inside of get a significant radiation dose from these gamma rays, you need to be within meters of the beam. So really in the core of the thunderstorm where things are being generated. But I also looked at, since we have gamma rays propagating into the stratosphere, can they produce nitrous oxide, NOx? Can they contribute to depletion of ozone? And the short answer is no. So left here is just the atmospheric profile. And on the right is, from my simulation, I basically took the total energy in the TGF between the ozone 15 kilometers and 15 and 35 kilometers, which is the edges of the ozone layer. So I took the total energy of the TGF, kind of did the back of the envelope calculation where if you assume that all those runaway electrons go into dissociation of nitrogen, which produces NOx, it's kind of like a worst case scenario where every electron will produce a NOx molecule. You'll get you basically can take the total energy of the TGF, multiply it by the grams of nitrogen, and how many TGFs per year should be detected, or how many TGFs globally per year are produced based on the observations we did with Fermi. We can extrapolate how many TGFs per year we should observe, and the number comes out to about 14,000 kilograms. And if you compare that with other sources of nitric oxide, even from lightning itself, we're on the order of teragrams, so very small contribution to nitrous oxide. But we published this result because people were asking and curious, can this contribute to the nitrous oxide and the destruction of the ozone layer? So it was a pleasure really to work at FIT. We did really cool stuff in terms of capturing lightning and gamma rays from aircraft, from using satellite data, drones, balloon experiments. And it was just really cool to just be out there, and we even did ground campaigns where we had one of these terror boxes in our car, in one of our vans. We drove around Florida trying to capture these X-rays and gamma rays. We had meteorologists on the phone from Florida Tech, and they were telling us where to go. We had a 20-second clip on the Weather Channel showing us going and chasing lightning. So in summary, basically, lightning is not just an optical phenomenon, but it produces radio waves, produces X-rays, gamma rays, antimatter, and the exact mechanism of TGF production is still under debate. We think we understand the relativistic feedback effect of how those avalanches are produced and produce the X-rays and gamma rays. And future research, I showed you Dr. Nag's work. He's really trying to understand TGF production and how that's related to high peak current from lightning, and are TGFs more intense over water and land, and how they're associated with hurricanes. All this research is a collaboration effort between meteorologists, atmospheric scientists, particle physicists. So it's a really expanding field. And I've had an idea for a long time where we have a ton of these terror boxes still left. The facility at Camp Landing, basically our grant ended there, so we're not really doing the rocket triggered lightning there anymore. But we still can deploy these boxes in stations, say, and try to detect natural gamma rays from natural lightning. And so one of the ideas that myself and some colleagues have had is, can we disperse this array over Florida, UCF, University of Miami, USF, and try to produce a network of lightning instrumentation here in Florida, since we are the lightning capital of the world, of the country. And so that's an idea I'd like to bounce off you guys. If you guys are interested in doing some kind of lightning research here, come and talk to me. And so I'll leave here. I get this a lot, so I figured I'd end with a cat meme. I get at, why do you study lightning? No, I study lightning. So just wanted to throw this in here as a final pitch here. So I'll take any questions you guys have, and I really appreciate you guys' time for having me here.
We got to go to a meeting.
Sure.
Thank you.
Mm-hmm.
Introduction.
Yep.
When you did the rocket lightning,
Yeah.
did you have to notify the pilots, or
No. So these rockets would go about 1,000 feet. We would have to notify the ranger that was on site for the National Guard, because it was their land. So we had if there were training exercises going on, if they had to be aware of what was going on. What I didn't mention is we fired one of these rockets through a whole summer campaign. We'd have about 10% success rate, kind of low compared to the number of rockets we would fire. A lot of times what would happen, we'd fire the rocket and lightning would occur somewhere nearby that would just kind of kill the field. So you wouldn't get an initiation. You get those positive streamers that I showed from the nose cone of the rocket. You would get those called precursors, but you wouldn't get an actual attachment to the ground. So we had to go and find the rockets and reuse them, and so it was a lot of fun just being out there. But of course, the grad students were the ones going out and arming the equipment. The X-ray camera was on power, like ground power, but obviously when we would fire a rocket and have lightning strike 20 feet away, unplug power, put on battery power, so we'd have to go out there and in the middle of a thunderstorm and kind of do all that. But it was fun. It was great.
How many TGFs, like how often do they happen in storms, like on average?
Yeah, so let's show this number here. So the estimate is about 400,000 TGFs per year. Daily, I'd have to go back and give you a number.
Okay.
But they happen often enough to that we have a database of a ton of these things, and also have been detected on the ground naturally as well.
Yeah. That's
and when we say
yeah.
TGF, I showed the X-ray emission, and X-rays were like hundreds of keV to 1 to 2 MeV. When we say TGFs, we really mean that distinct photon energy spectra where it cuts off at like 30 or 40 MeV. That's really what's classified as a TGF. There's a big debate in the field too. What is a TGF? How do we classify it? Is everything a TGF, or is there a certain population that's just TGFs? But they occur often enough, and lightning strikes about 40 times per second on Earth. So how often a TGF would occur?
So were those rockets positively charged?
So
Did it attract the lightning or what?
yeah, it would attract the lightning from the copper wire that we spooled on it. So the copper wire was grounded, and so we basically have this big copper wire. It's grounded to Earth, sticking up in the air. So the lightning leader would come down and meet that.
So you were
And
making a giant
lightning rod, basically. Yep.
So you don't need a rocket for that. You could theoretically just.
Well, you could, but the problem we wanted to get high enough in order to meet that negative leader coming down. So you could have a lightning rod in your house, but it can rarely get struck. This we were, again 10% success rate too, which told you a lot, because we have a ton of events, but not as many as we hoped.
I have another question about the positron.
Yeah.
So was the thing about the antimatter production that you're producing electrons as well in the antimatter production, and those are what caused the avalanche?
Yes.
Because the positrons will just annihilate
Well,
the electrons.
They will, but if let me show you here. Yeah, they will, but if you have positrons that are produced short enough, they can basically, so the electric field is pointing this way, so that you have electrons accelerating down. Some of these positrons have the probability of getting back to the original location or somewhere in this region and producing they'll annihilate, but you also have that positron then will produce positron and electron will annihilate, produce a gamma ray. That gamma ray then produces another electron avalanche.
Okay.
Yeah.
That's what I was wondering.
So it's not like it's not a one step. It's like a two-step process.
Annihilation produces light.
Yeah, it produces a photon. Yeah. So then you get, and that photon then can produce another electron. So yeah. So main takeaway there is that thunderstorm is a particle accelerator.
Yeah.
Yeah.
I have one last question. I'm
Sure.
sorry. What's the percentage? In lightning, it emits all sorts of light. Is it mostly gamma, or what's the percentage of
A lot of-
X-rated gamma
yeah.
versus optical?
That's a good point. I don't know the answer to that, but a lot of the energy that's deposited from lightning actually goes to heat.
Okay.
Heat expansion of the air, which produces thunder. Right. So that's the most dominating component of lightning. In terms of X-rays and gamma rays compared to optical energy, I don't know the percentage. But if you're worried about getting, if you're nearby in a lightning strike and don't get hit, even people who get hit on the ground probably aren't getting a significant dose. Again, because the lightning has to travel pretty far through the atmosphere. Reason TGFs have so much high energy is that you have the air is less dense up and their probability of escape is way more. but you probably can receive a chest X-ray if you're close enough. But the attenuation length of X-rays are pretty small too, so you have to really be close or be struck.
Okay, then thank you again.
Thank you.
And thank you all for coming. And this was the last semester, the last seminar in this semester.